Welcome to Primary Stream Components. My name is Angie Corson, and I'm the Streams Program Coordinator for the Missouri Department of Conservation. Today, I'm going to be talking about some very basic principles on how streams function. This will give you a basic understanding of the physics of stream functions that will further be explained in the rest of this Understanding Streams series. So you are listening to the Primary Components talk. This is part of the Understanding Stream series of talks. You may have already heard some about primary components in the talk, What is a Watershed, if you've watched that already. This one will go into a little bit further detail on primary components. There are four primary components that interact in watersheds to create and maintain stream systems. They are sediment, water, vegetation, and energy. And when there is a change in just one of these components, it's very likely that the other components will be affected by that. Together, these components balance to form what we know as a dynamic equilibrium in a stream. So changes in any one of these components can affect the other three, which then causes changes within the entire stream system. This is called connectivity, which is inseparably linked systems functionally supporting each other. And changing one in the system causes a reaction in all the other systems. So here's a video that we will be looking at. And I like the still shot of it because it really clearly depicts our four primary components. Obviously, we have the water component, which is running through the channel and beginning to spill out onto the floodplain. We have the vegetation component, which is very important, and that's noticed in the trees and the grasses and the brush that is both in the channel and out into the floodplain and riparian zone. And then we have the sediment, which may not be so obvious, but notice how muddy the water is. That water wouldn't be muddy if it wasn't carrying sediment, even though those are fine soil particles and silts and sands. Below the muddiness, there are gravels and cobbles being moved as well. And then last but certainly not least is our energy component. And this stream would not be flowing if it weren't for gradient or slope, which provides energy to a stream, starting at the very top of the watershed in the uplands and moving downhill from there. So let's watch as our primary components interact in this bank full stage rainflow event. Again, notice the water moving downstream as our energy, the vegetation interacting with the water and the sediment moving through the channel, and the volume of water that's in there as well. So these are all very important, and we're going to look at them again in a simplistic fashion, but to really understand how they work with each other in their connected ways. The term dynamic equilibrium is often used to describe a stable stream reach. And the definition of dynamic equilibrium is if over time the amount of sediment that leaves the reach equals the amount that has entered it, again, it's considered in dynamic equilibrium. So basically, we all understand that you never step into the same stream twice. The water's not the same, the sediment has likely moved, and it changes over time. But if it's doing so in balance, then the stream can remain what we would consider stable. This is Lane's balance. This model does a nice job of demonstrating a simplified example of how water, sediment, and energy react to changes within one another. We can't forget, though, one of our most important components, which isn't currently demonstrated on this model, and that is vegetation. Without the vegetation component, all of the others could quickly become off balance, and it could swing wildly in one direction or both. And this is because vegetation does a lot of things. It absorbs water, it slows down runoff, and it helps to lock down sediment in the watershed that could otherwise get in the channel because of its root systems. So we really don't want to forget the overarching vegetation component's effects on the other three components and how it acts to keep them in balance, or what we call dynamic equilibrium. So now let's play with our model. For now, we will just see conceptually what happens when we change each of these primary components. But later, in some of the other videos within the Understanding Streams series, you will see real-life examples of what can actually cause these different changes. So for this one, what happens when the gradient or the slope of the stream is steepened? Well, let's find out. We move our bucket to the left, and as you can predict, our balance tips. And notice where the arrow points. It's pointing to erosion. So by increasing the gradient in a stream, it actually increases the energy or the velocity of the water, and the channel responds by having a lot more erosive power. This can cause the stream bed to erode and insize or deepen. This is often called head cutting or down cutting. That can then cause the banks to be much more tall and vertical, and it makes them a lot easier to then erode and fall into the creek and thus widen the stream channel as well. So now let's see what happens if we decrease a stream's gradient. In doing so, we're going to move our bucket over towards flat, and you can probably guess what's going to happen next. You probably guessed it. Deposition is what we can expect to happen. And this is when the stream channel begins to fill with sediment and becomes more shallow and often has to widen in order to accommodate the extra sediment. So the deposition that we just talked about actually increases, again, the amount of sediment in the stream channel. So let's see what happens to our scale as that occurs. As you can see, we've put a lot more sediment on the tray, and what do you think we can expect? You probably guessed it again, deposition. So once again, we have the channels filling in. Sometimes old swimming holes or pools will now fill in with extra sediment and become more shallow as well. This can also cause some stream channels to have to abandon their old channel and form a new one through the floodplain to be more efficient. So, much like sediment can be increased in a stream reach, sediment can also be decreased by certain practices. Let's see what happens when we decrease the amount of sediment on our balance. Our scale now points to erosion. So we can once again expect erosion, perhaps both in the stream bed and in the stream bank as it tries to regain its equilibrium by adding more sediment to the stream. Now let's move over to our water component, which is in our bucket. What will happen when we increase the amount of water that is coming into the stream system? We raise the water in our bucket, and once again, we tip the scale, and this time it points to erosion. So we see similar types of erosion of the stream bed and the stream banks from increasing the volume of water in the stream channel. Now we will decrease the amount of water in our bucket and see what happens. And we turn our scale to point to deposition now. So a decrease in the amount of water in a system can actually fill in the channel, and the channel responds by getting smaller sometimes and growing more vegetation. Let's shift over to look at our sediment again. This time, let's look at the size of the sediment in the stream channel. There are times when we can actually change the size of the sediment due to different practices occurring in the stream as well. So we're going to enlarge our stream sediment this time. And we can see that by enlarging the stream sediment, we get deposition. And this is because it will now take more energy to erode that sediment. And if the stream has the same amount of energy, it can no longer push those larger grains of sediment, and therefore it will slow down and begin to deposit. And last but not least, let's take our sediment again, and this time we're going to remove the larger sediment and just leave the smaller, the fine particles of sediment and see what happens. So as we make it smaller amounts of sediment in the stream, and you can see that our scale once again tips towards erosion. And this is because when we move the larger materials, which were actually adding friction to the stream, we now have less friction to eat up some of the stream's energy. And since the water component hasn't changed in the amount of water coming through, the stream has more power to erode now. So this concludes the primary components talk, but in summary, understanding the primary component connections, water, sediment, energy, and vegetation, we can now see how one change in the system can cause the others to react. And this connection will be a common theme throughout the other videos that you will see in this course that will go into more detail and explain them with examples more thoroughly. Thank you for watching.